Welcome back to Calculus 1. In the last lesson, we used implicit differentiation to find derivatives when x and y appear together in one equation. Related rates problems use the same idea, but now the changing quantities are functions of time. We will connect those quantities with an equation, differentiate that equation with respect to time, and use one known rate to find another. The goal is not simply to calculate a derivative. It is to interpret what the derivative tells us about a situation that is changing from one moment to the next. Let's get started. Here's what we will cover in this lesson. First, we will see how two changing quantities can be linked by a familiar equation. Next, we will differentiate that equation with respect to time so that the equation links the rates of change. We will then translate statements such as the radius grows or the side shrinks into derivative notation. Finally, we will use geometric relationships to solve problems involving circles, balloons, ladders, moving cars, and cone-shaped tanks. The chain rule is still doing the work. The difference is that each changing quantity now depends on time. Imagine dropping a stone into still water. As the ripple spreads, its radius increases, and its area increases with it. The two quantities are connected by the circle area formula. Area equals pi r squared. Because a and r change with time, differentiate the equation with respect to time. The derivative of a with respect to t is equal to 2 pi r times dr dt. This equation links the area rate to the radius rate. It also shows that the area rate depends on the current radius, not only on how quickly the radius is growing. That is the central idea of related rates. An equation connecting changing quantities also connects the rates of change. Related rates problems follow the same 4 steps. First, draw and label the situation. Identify which quantities change and which measurements remain constant. Second, connect the changing quantities with one equation. Third, differentiate both sides with respect to time. Fourth, substitute the known values and solve for the requested rate. The words tell us the notation. A radius growing at 2 feet per minute means dr dt equals 2. Water entering at 9 cubic feet per minute means dv dt is equal to 9. A side shrinking at 1 centimeter per second means ds dt equals 1. A negative rate means the quantity is decreasing. A question asking how fast the area changes is asking us about dA dt. Keep every changing quantity as a variable until after differentiating. The order is draw, connect, differentiate, and then substitute. Let's compare two examples in which the given rate is constant, but the rate we want depends on the size at that moment. For the spreading circle, the radius grows at 2 feet per minute, and we want the area rate when r is equal to 15. Begin with a equals pi r squared. Differentiating with respect to time gives dA dt is equal to 2 pi r times dr dt. Substitute r equals 15 and dr dt equals 2. The area is growing at 60 pi square feet per minute, or approximately 188 square feet per minute. For the balloon, air enters at 100 cubic centimeters per second, and we want the radius rate when r equals 5 centimeters. Begin with v equals 4/3 pi r cubed. Differentiating with respect to time gives us dv dt is equal to 4 pi r squared times dr dt. Substitute dv dt equals 100 and r equals 5, and then solve. The radius is growing at 1/pi centimeters per second, or approximately 0.32 centimeters per second. In both examples, the given rate is constant. The rate being found changes as the size changes. Now it's your turn to find several related areas. Pause the video now and work off for problems, then continue when you are ready to check your answers. Let's check your answers. For problem 1, the area is growing at 60 pi square centimeters per second, or approximately 188 square centimeters per second. For problem 2, differentiating the cube volume formula gives dv dt equals 3s squared times ds dt. Substituting s equals 4 and ds dt equals 0.5 gives 24 cubic inches per minute. For problem 3, differentiating y equals x squared plus 1 with respect to time gives dy dt equals 2x times dx dt. At x equals 3 and dx dt equals 4, the result is 24. For problem 4, ds dt equals negative 1 because the side is shrinking. The area rate is negative 40 square centimeters per second. The negative sign does not mean that the area is negative. It means that the area is decreasing. Each problem uses the same core moves: connect, differentiate, and substitute. Now let's consider a 13-foot ladder leaning against a wall. Let x represent the distance from the wall to the bottom of the ladder, and let y represent the height of the top of the ladder. The wall and the ground form a right angle, so the Pythagorean theorem connects the variables. X squared plus y squared equals 169. Differentiate both sides with respect to time. 2x times dx dt plus 2y times dy dt is equal to 0. At the instant in question, x equals 5 feet and dx dt equals 2 feet per second. The 5, 12, 13 triangle tells us that y equals 12 feet. Substituting those values and solving gives dy dt equals negative 5/6 feet per second. The negative sign confirms that the top of the ladder is moving downward. The ladder's length remains constant, so differentiating 169 gives 0. This example adds one more important geometric step. The cone is 6 feet tall with a top radius of 3 feet. The water forms a smaller similar cone, so the radius of the water surface and the water depth satisfy RH equals 3/6. Therefore, R equals H divided by 2. Substitute this relationship into one cone volume formula before differentiating. V is equal to pi h cubed divided by 12. Now differentiate with respect to time. dv dt equals pi h squared divided by 4 times dh dt. At the instant in question, dv dt equals 9 cubic feet per minute and h equals 4 feet. Substituting gives 9 is equal to 4 pi times dh dt. Solving gives dh dt equals 9 divided by 4 pi, or approximately 0.72 feet per minute. The similar triangle relationship is what allows us to replace r and write the volume using h alone. Now it's your turn to solve 3 complete word problems. Begin each problem with a picture, label the quantities that change, record the known rates with their signs, and identify the relationship connecting the variables. Pause the video now, draw each picture, and work all 3 problems before continuing. Let's check your answers. For problem 1, the bottom is 7 feet from the wall, the top is 24 feet high. Substituting into the differentiated Pythagorean relationship gives negative 7/8 feet per second. The negative sign means the top is sliding down. For problem 2, the cars are 30 and 40 miles from the intersection, so the distance between them is 50 miles. Differentiating the distance relationship and substituting the 2 velocities gives 100 miles per hour. For problem 3, r is equal to h divided by 3, so the cone volume formula becomes v equals pi h cubed divided by 27. At h equals 6 and dv dt equals 5, the depth is rising at 5 divided by 4 pi feet per minute, or approximately 0.4 feet per minute. Problems 1 and 2 use a Pythagorean theorem. Problem 3 uses the cone volume formula together with a proportional relationship of r equals h divided by 3. In every case, the picture identifies the equation that connects the changing quantities. Let's bring the main ideas together. A related rates problem involves quantities that change with time and are connected by an equation. Differentiating that equation with respect to time creates a new equation connecting the rates of change. The 4 steps are draw, connect, differentiate, and substitute. The habit that prevents the most common mistake is keeping every changing quantity as a variable until after differentiating. The sign of a rate also matters. A positive rate means the quantity is increasing, while a negative rate means it is decreasing. This completes chapter 2. We have developed the differentiation rules and applied derivatives to quantities changing in real time. Thank you for watching. In this lesson, we connected changing quantities with equations and differentiated those equations with respect to time. We used known rates to find unknown rates in problems involving area, volume, distance, and motion. The central strategy is always the same: draw, connect, differentiate, and substitute. I'll see you in the next chapter.